Okay, so let's start the class. Do remember that we have a test next Tuesday in person on paper, and then you have a review test in Dropbox, right? And that if you have a DRC, you need to contact them, you, not me, because I have tens of students. I cannot do that for each one of students who are at the DRC. So you have to contact them, remind them, because otherwise they always forget. And then they contact me, and then I send them the test. And then you take it over there, and then they send me a scan. So make sure to do it. Okay, I cannot stay beyond the time. I cannot stay because there is a class anyway on Tuesday. So again, if you have the GRC thing, you have to contact them. It's you, not me. Okay, multiple choices. Do bring the equation sheet. Do not forget. And do bring a calculator. And there is a review test. And the review test does not apply for makeup. I explain why. So anyway, if you missed the class on Tuesday, it was an important one because we touched on vector calculus. So make sure you ask the notes from someone. You can always try to go back 1 year ago, but I always have some modifications. So make sure you catch up. I know some students here, I don't want to say name, but they take really, really good notes. So you just have to pay for a coffee or something and get the notes. So if you miss the class, make sure you catch up. Okay, so last thing about vectors again. Let's review a last time. If you have two vectors, okay, and you want to add them up. So for example, you have this vector, you see it has a x component, it's negative, a y component. So you go from the tail to the head. So you go to the left and then you go up. This vector also has a x component, you go to the right, a y component, you go up. Shh, quiet. And I just want to remind you, you have two ways to add them up. I just show you so far one way, which is called tail to head. So you have your two vectors. Let's say these are my vectors. You take one, paste it on top of the first one, tail to head. And then you're going to connect the tail of the first to the head of the second. Okay, so what you do, you take one, doesn't matter which one you take. Okay, you paste on top of the first one, and then you connect the tail of the first, the head to the second. That's going to be your sum. Okay? Algebraically, to find the x component of the sum, you add the x components of the first and the second vectors. To find the y component of the sum, you just add the y components of the individual vectors. Is that clear? Each time you have a vector, you need to attach its tail at the origin this way. So you want to make sure to have the right angle. So for example, here we are in the first quadrant, and you want to know exactly which angle you're going to find when you use tangent. Okay? Because you don't want to confuse the angles because they are complementary. They add up to 90 degrees. So you want to make sure to trace your vector in the XY coordinate system to know in which quadrant it's gonna lay. Okay, for the magnitude is no problem. You do Pythagorean theorem. But for the direction, it can be confusing sometimes. When you are doing arc tangent, you are not using minus. Okay, you forget about the sign. You just do opposite over adjacent. Is that clear? Okay, so for example, if you end up with a vector like this, okay, that will be in the fourth quadrant, and you can find this angle. So that's called tail to head. Now, there is a second way, maybe in your textbook, they will use this one. It's called the parallelogram method. So parallelogram method, you have a vector A and a vector B. And now you're going to attach them by their tails, so they don't go on top of each other. Just attach them by their tails here, and you're going to trace a parallelogram. So this is a parallelogram. Opposite sides are parallel to each other. This side is parallel to that one, and you trace the diagonal. Okay, and you will get the same thing. Okay, so you have tail to head or the parallelogram method. Is that clear? So first method, tail to head. Second method, you attach them by their tail. You see, you make your parallelogram, okay, and the diagonal will be the sum. Tail to head, obviously, that will be tail to head. You connect the tail of the first to the head of the second. I invite you, of course, to open the textbook, do the solve problem, and read along, especially if you want to be an engineer. So that will be adding. Last time I explained, so that's why you want to go back if you miss the class. If you want to do A minus B, A minus B, you go from the second vector to the first. So you attach them by their tail, so A and B. If you want to do A minus B, it's always from the second vector to the first. So the vector will go from here to there. You have a different way to do it, but you see it's the same vector. It will be in this direction. Okay? A minus B, you go from B to A. Is that clear? I have posted that simulation if you want to play with it. Okay, so we did that last time. And we talked about circular motions, very important in to understand how it works. So if you have a uniform circular motion, okay, we define the speed, which is the distance around, okay, over the time it takes to go one cycle, once around. This is called the period, okay? This is the radius. So that will be in meters. This is in radians, but radian doesn't count. And you can write that as this quantity here is called omega. So it's how fast it's spinning. It's the rotational speed. Okay, so it's like revolution per second, for example, except that's going to be in rad per second times r. Okay, and then remember that if you have a distance around of 2 pi r, so the distance around a circle, one circle is also 360 degrees, which is also 2 pi radians, and which is also 1 revolution. So you can use proportions to change the unit. Okay, what else? Okay, so for example, if you have 33 revolution per minute, that will be the old vinyl, for example, that will be the same thing as 33 times 2 pi over 60. So that will be rad per second. Okay, the distance around will be 33 times 2 pi r. Okay, so because you take a string, so if you want to find the total distance, you take the string, you go once, twice, 3 times, 4 times, 33. Okay, so we did that last time. So I highly recommend that you catch up if you missed. Okay, so here we have a uniform circular motion. Uniform meaning there is no speeding up or slowing down. So it's moving at a constant speed, but there is an acceleration because the velocity is constantly changing direction. For a velocity to change direction but not changing the magnitude, you need to apply a force perpendicular to the velocity, and we call that the centripetal force. Okay, So it's just a review. Uh, Again, if you miss the class, you need to catch up. Right? Now, remember that an acceleration is just a force per unit mass, but they both have the same direction. Okay, acceleration and force, you should put net force, they both have the same direction. So if you have a force here, which is called the centripetal force, that means you have an acceleration which is called the centripetal acceleration. And we on Tuesday, the magnitude, we saw that the magnitude was the speed square over the radius. So typical conceptual equation, that means if you multiply the speed by 2, the acceleration will be multiplied by 4. Speed is multiplied by 3, acceleration is multiplied by 9. So it can be very deadly. If you speed up on the highway and you make a turn, chances are that you're going to go off tangent because you're not going to have enough friction to provide the centripetal force to keep you on the track. Inversely proportional to the radius, which means that a sharp turn, okay, sharp turn, you need more force to keep you on track. So if you multiply the radius or you divide by 3, the radius, so very sharp, then the acceleration will be multiplied by 3. You need 3 times the force. Okay, so it's just a review. Is that clear? Note that mass, we're going to see that next. Mass is inertia, is laziness. So it means if you have a large mass, okay, it means that the acceleration will be smaller. So a large mass will be harder to bend, harder to curve. Okay, so a truck will have a harder time to make the turn than a bike. Okay, so okay, so that's a review. So acceleration is the force per unit mass. So we did that last time. Uh, okay, so we did that, and we were talking about Space Odyssey, which was a masterpiece. And you see in that movie, that spacecraft here, it's not a spacecraft, it was a space station. And if you are in a rotating space station, a rotating frame of reference, inside that frame, you're going to feel a centrifugal force, right? You're going to be pushed outward. And if it goes at the right speed, okay, that force will be exactly equals to your weight. So that way you can simulate gravity. Okay, yeah, you can see that in, you have some, I don't know if I have them here. Here, you see those crazy rides here. Okay, they spin you, and all of a sudden you feel push on the outside, and some crazy kids sometimes they are able to stand up on the wall, right? Because if it spins fast enough, it's like gravity, and then they remove the floor, and you stay on the wall. So this is very cool. So the same idea, same idea. Not that everything here is spinning at the same rate, but if you are standing there, you are not going any, the speed will be equals to 0, right? Because you just speed, you spin on yourself, and you are not going to feel that centrifugal force. So anyway, let's just do this problem here. So let's say the space station here was 150 meters in radius. How fast should it be rotating or spinning So people will feel gravity and they are not getting osteoporosis, right? So when you are in space, the issue is that you are not able to fight against gravity and you are losing your bones. That's what happened to the astronauts last year when they were stuck for 6 months. I don't know for how long. Like, so that's why this is the best way to do it. So people are not losing their bones. So anyway, can you do that problem here? I'm taking tangent. Okay, so you have your space station here, and you are there. Yeah, it's spinning. So from your point of view, only from your point of view, okay, you're gonna feel artificial. It's artificial. Artificial gravity because it's in space. Okay, there is no gravity. But if it's spinning at the right rate, so omega, right? So if it's spinning here and the radius is r, then you're gonna feel your your weight here. Okay, you're gonna simulate gravity. That's your weight. So you're doing it. So the equation is the acceleration is v squared over r. And you want that to be equals to g, which is 10. So you want to know how fast the space station has to spin such as gravity is simulated. So you can walk. You're actually walking here. You can walk on the wall and you don't even know that you are upside down. You can walk here. What did you get? 39. 39, yes, 39. Do you all find that? So 10 equals speed square over 150. So the speed here should be 39 meter per second. What? So that will be 39 meter per second. That will be your linear speed. Okay. Now, if you want to turn that into omega, so then you go V equals R omega. And then you can find the revolution per second, for example, right? So if you want, okay, so you can do omega equals 39 divided by 150 rad per second. So one rad, how do you convert to revolution per second? So 2 pi is 1 revolution. And then you can find in revolution. 1.8, almost 2 revolutions per second. What about per minute? Multiply by 60, right? No, it's divided by 60. This is per second, isn't it? Per second. Okay. So anyway, in meter per second is going to be 39 meter per second, which is about 90 miles per hour. So it looks fast, but that's what you need to simulate gravity. Okay? Is that right or no?
What do you mean by 150 square?
150?
You said 5 feet, so what do you mean?
Because it says 150 here. The 5, 150 meters. Because I want in meters. Okay? So that will be the speed in meter per second. Okay? And in the movie, this is HAL, right? It's the evil computer. So anyway, that will be the way you simulate gravity. Okay, so this one is easy. So is it A, B, C, or D? Did you all do it? See, very good. See, very good. As centripetal acceleration is v squared over r. So this is 4 and 50 squared over r. So you cross multiply divide. So if you want to find revolution per minute, you have to multiply by 60. Okay. So if you want the answer here, okay, that will be so 0.3 divided by 2 pi. So if you want that in revolution per minute, okay, you will do 0.3 times 1 divided by 2 pi times 60. Okay, because one minute is 60 seconds. And if you find that, you find 3 revolution per minute about. So it could be possible, right? 3 revolution per minute. It sounds very fast, but why not? If it's very, very large, okay, you won't feel the Coriolis effect, so it's not that impossible. So I looked it up because I was curious. Do you agree with that? In 1 second, so 60 seconds, you multiply by 60, right? Yeah. If you have revolution per second, if in 1 minute you're gonna have more revolution, right? And I look it up. So Stanley Kubrick, when he did this movie, it was not 3 revolution per minute. It was like more like one revolution per minute. So people will feel like on the moon if you do the computation. So it was not like on the Earth. So anyway, that's a tangent. Okay, let's move on. So do the computation for next time. And if you don't get the right number, we'll do it together again. Okay, so if something is going around, sometimes instead of using this equation, you can use this one. Do you agree? So that will be your speed. You plug it in, okay, and you're gonna get this. So sometimes it's easier to use that. Okay, so let's just plug it in to make sure you know how to use scientific notation. It's a nice review for the test, right? Clear? So 4. So let's do it together. 4 times pi. Pi what? Pi square. Okay. Times the radius. Radius is 1. No, sorry. It's going to be 1.5 times 10 to the 11. Don't wait for me, okay? little bit slow. Okay, divide by, and remember what I told you? 1 year is pi times 10 to the 7. So 3.15 times 10 to the 7. So 3.15 in seconds times 10 to the 7. Okay, and you square that. Did you all get that? Remember, in 1 year you have 365 days. In 1 day you have 24 hours. In 1 hour you have 3600 seconds. If you multiply those numbers together, you get pi times 10 to the 7, or 3.15 times 10 to the 7. So that way you do it in one strike, okay? You don't have to do the steps, you do it on your TI. The time is the Earth goes around the sun in 1 year. Oh yeah, they don't say that. You're supposed to know. 1 year to go around the sun, 365 days times 24 times 60 minutes times 60 seconds. Okay? So the answer is this one, A. Right? Any question? Any question? Good. Okay, question here. Conceptual question. What happened to the bicycle if the speed is multiplied by 2? Multiplied by 4. So the answer is A. Do you all agree? So typical conceptual question. That's why it's lethal. It's very important when you are driving, slow down when you are making a turn, okay? Because the force that you need goes with the square of the speed. So that's why you can kill people. Not cool. The direction of the instantaneous velocity of the ball is always perpendicular. Very good. No, no. Tangent. Tangent to the circle. Yes? Okay, so if I go back to here, acceleration is perpendicular to the velocity, but the velocity is always tangent. So instantaneous velocity is always tangent to the trajectory. The velocity is always tangent to the trajectory. Okay, so remember a projectile motion. So if you have a projectile motion here, something like this here, then the velocity here is always tangent, but it has two components. X component, which is always staying the same, and the y component that will decrease at the rate of 10 and then increase again. But it's always tangent. So instantaneous velocity is always tangent. Agree? Okay, so then you have non-uniform circular motion. So non-uniform meaning you can speed up and turning, or yes, so the speed is not constant. So usually when you are making a turn, you don't speed up, okay? You slow down. So you are doing two things at the same time, okay? You are changing the magnitude of the speed and its direction. But for any curve, you can have, like, it's called ausculting circle, which means kissing. The circle is kissing the curve here, right? So you can always attach a circle here and find the radius, the curve. Is that clear? So he's going this way, and then here he's spinning up, maybe the same speed, and then he's slowing down. So this is called non-uniform. So that's a question on the pop quiz. So have your listening ears. He's making a curve here. Do you agree? Now we can define two components of the acceleration. Those components are instead, we could have x and y, but it makes more sense to have a tangential acceleration and a radial acceleration. So remember, an acceleration is just a force. So this force here is parallel to the velocity. It's going to pull the car forward. So what do you think this acceleration is going to do? The car is going this way, and then you have a force from a thrust. Okay, the thrust is pulling the car or pushing. So what that force is going to do? Accelerate, making it go faster. However, you also have a force here from the static friction changing the direction of the velocity. So it's doing two things. It's spinning up, okay, because there is a force, there is a thrust parallel to the velocity, and there is also a centripetal force changing the direction of the velocity. Therefore, you have two accelerations. You have this component, which is called the tangential component, and you have the radial component. Okay, and then of course you can combine them together because it's a vector. Okay, so it has these two components, and you can find the magnitude. Is that clear? What's happening here at that point here? So the car is going this way. So the car is going that way, but now you have a force in the opposite direction. So what is it doing? Slowing down. Do you all agree? Okay, you have a constant velocity. If you have a thrust, it's going to move faster. If you have something opposing, it's going to move slower. Okay, so now the car is slowing down, but at the same time, it's making a turn. Okay, so you have two components. You have a force that will be in charge of changing the direction of the velocity, and you have a force which is in charge of slowing it down. And mathematically, in reality, in the real world, that will be your acceleration. But mathematically, to solve problems, it's easier to decompose the acceleration into two components with two different jobs. Okay, and then here you have another curve here, so you have this one and that one, it's still spinning up. Is that clear? So it's a question on the pop quiz today. So example, this is a car and it's making a turn. Okay, it's going this way because you have the instantaneous velocity. So think for 2 seconds. Don't be on your phone. Right? Think for 2 seconds. Is it moving at a constant speed? Is it slowing down or is it speeding up? Slowing down. Do you all agree? Because this force, acceleration is a force, is opposing the velocity. Okay, so it's slowing it down, the car, and this component here is helping it making the turn. Otherwise, off tangent it goes. Okay, so the acceleration has two components. You see, you can use vector sum. The magnitude is you use the Pythagorean theorem. Okay, so in engineering, for example, they use a lot of those concepts here. Okay, yes. What? A1, this one is tangent. It's not A1, it's tangent. So tangential component, it comes from your gas, the thrust. The acceleration of the car when you hit the gas pedal. It comes from burning fuel. Thrust.
acceleration or
Oh, sorry. So in that case, you are slowing down. So it comes from the brake. It comes from the friction, right? So this one comes from the friction. If you accelerate, if you speed up, it comes from the gas, the thrust. It has to come from somewhere. So that comes from the brake. Okay, and this one comes from the static friction, pushing the car toward the center of the curve. Is that right? Uh, it's like so. For example, if you have like those athletes like crazy and they run and they have a parachute behind them like this, right? So then the force that slow them down comes from the air resistance. So that will be the force here, and that will be also the acceleration will be also in that direction here. Okay, and the velocity will be here. Okay, so this is a summary. So here they are using vector notations. So instead of having a x and y set of equations here, they just packed everything in a vector notation, but it's not that hard to understand. Okay, good. The circle, which one? This one?
of that. When you thought of the zero.
Oh, but what they do is that they call that osculating circle. So you have a curve here, and then they call that a kissing circle. So they will make something like this, and then they will find this radius here. And for every curve, you can do the same thing. Okay?
Yeah. Trying to get the way so
Well, I don't know. You have to ask the surveyor engineer. They go on the field, they take a meter stick and they measure. I'm sure they have a modern way to do it. I don't know, maybe with a drone, for example, you can do it with a drone, right? And some computer software, but I'm sure, I'm sure it's a very easy thing to do. Ask ChatGPT. How do engineers find the radius of osculating circles along the road? I'm sure they do it using some electronics nowadays. It's a good question, but I don't have the answer. Uh, it's called surveying. It's part of the civil engineering, and they know how to do it. Okay, just an example of application. If you work in a lab in biology or chemistry, you have something called a mass spectrometer. So it's a way to, so you have some ions. So let's say they have the same charge. So it's a way to separate them according to their mass. Okay, so based on their mass, they are able to separate them. So how they do that? Because you have a charged particle inside a magnetic field will experience a force, but that force will be a centripetal force. So any charged particle inside the magnetic field will be curved. But how much curving it will get depends on the mass. Why? Because you remember acceleration is the force per unit mass, right? So acceleration is the force per unit mass. So if you have a large mass, Okay, it's not going to curve as much as a small mass. A small mass will experience more change in the state of motion. So the velocity will change more in directions. So this is called a mass spectrometer. The centripetal force is provided by a magnetic force. Okay, so back then, mass spectrometer, before World War II, they came up with it. But then during World War II, they were working on the bomb, the atomic bomb, and they used the idea to enrich uranium. That's how they started to enrich uranium with a mass spectrometer. Okay, that's a tangent. Let's go back to our business. Oh, I forgot to show you something very quick because a student sent it to me a long time ago. Do you remember how I told you that we are used to 1g? 1g is our own weight. So, for example, if you take off with an airplane like a very fast airplane, then you're going to experience 3g, for example. That means 3 times your own weight. You cannot go over 10g. Okay, 10g you die because blood doesn't get to the brain. 7g is already, I mean, anyone will pass out, right? You have to be very experienced. And that's what this video is showing you. So F18, very, very fast, right? A lot of acceleration. She passed out. Did you see that? She passed out. You see, she take it very cool. Uh, so 7g, it's a lot, right? Because that will be 7 times your own weight pushing you, and the blood doesn't get to the oxygen doesn't get to the brain. And that's what, did I show you this one? I find it very cute. So if it's a question on the pop quiz, by the way, remember that the speed, so the distance over the time depends on the radius. So the one on the edge will go faster than the one in. Do you agree? Because it's proportional to the radius. So if you multiply the radius by 2, you multiply the speed, okay, the velocity which is tangent to the circle by 2. Okay, so when we were your age, we didn't have social media, we didn't have internet, so we were bored. So that's what we will do. Okay, we will take a vinyl records at the time. That's what we used to listen to music, and we will do things like this, and then we will spin the record very quickly, and off they will go. But they will not be harmed. So don't worry. So that's cute. Okay, any question on that unit? Can we move? So we're going to move from kinematics. So for the test, it's only kinematics 1D, kinematic 2D, and vectors. Okay, so now we are moving to unit number 4. Okay, we get to Newton's law. And we get to dynamics, right? So kinematics only deal with motion. Dynamics, it's going to look at forces that causes the change in the state of motion, the change in velocity, the acceleration, and mass. Because the amount of change, the speeding up, the slowing down, or the turning depends on the mass. Okay, as I've said, the mass spectrometer, you know, if the mass is large, it's harder for the magnetic field to bend. So mass is called inertia. And it was understood by Galileo, right? He understood that mass is the laziness, sluggish something will be more sluggish, will react not the same way to a force. It's called inertia. That term was introduced by Kepler. Johannes Kepler came up with the word inertia, but it was developed, of course, fully by Newton. That's why it's called the Newton law. So mass, that physical quantity, the unit is kilogram. Kilogram, and it's really the amount of stuff that you have, the amount of molecules. So if you go to the moon, your weight will not be the same, but the mass will be the same. And the laziness, okay, to change velocity will be the same. Okay, so forces, you have different kinds of forces. You have contact forces, right? So need to be touched. And then you have forces at a distance that will happen when you have some kind of field. So for example, on Earth, we have a gravitational field. So the Earth is generating an aura. We call that the gravitational field. And if there is a mass inside that field, it will react to that force, and that will be called the weight, the pull due to gravity. Okay, so it's not the Earth does not have an invisible arm and reaching out to a mass and pulling it toward it. There is a gravitational field. Same thing for the electric field. Positive and negative will attract, positive and positive will repel. This is because you have an electric field and you have a magnetic field as well. So these are called field force. Okay, so here are the kinds of forces we're going to deal with, right? Gravitational force, it's the weight. You have the buoyant force in a fluid, friction force, static friction, kinetic friction, tension along a rope, for example, a spring force, if you have a spring, obviously, and the normal force, which is the support force. Okay? Okay, so the unit for force is the Newton, which means kilogram times meter per second. So you guess that force equals ma. We're going to define the net force. The net force is the vector sum of all the forces acting on the mass. Okay, so first we need to find the vector sum. Okay, and then you can find the acceleration. Is that clear? So a sum, a force is a vector, right? It has a magnitude that you can measure with a spring scale, and it has a direction, and it has a unit, which is the Newton. Okay, so for example, here you can find this angle here if you are using tangent. The magnitude you can use Pythagorean theorem. Okay. Now, forces come into components. We already did that. Now, to understand now is that each component has a different job. Okay. So, for example, to make it more realistic, if I find, yeah, this is me here. I'm pushing, right? All of a sudden, everyone is interested. Okay, let's make it smaller here. So how we will deal with that? First of all, you can draw, okay, there is a force here and there is a force here, right? So that will be a push, right? Now, instead of having to draw the box, we're going to make a free body diagram. So we have a X, Y coordinate system. This is a free body, obviously. Diagram, that means I'm going to remove the box. So we are interested in the box. So the box is going to be here, okay? And it's going to be acted by a force here, the push. Now, the way we're going to do it, we're going to make sure we understand where is the force. So you can make a cross here at the tail. And you see the force is in the first, the second, the third, or the fourth quadrant. Third, very good. So it's very, very important to identify this. So now you can make a force here. Actually, there is two. So there is one force and then there is another one, right? They have about the same direction. That will be my push here. That force is going to come into two components. You can see that here. One component here, F sub x, is in charge of pushing forward. Okay, is in charge of providing the forward acceleration. But there is another force, another component that will do what? Push it down. Very good. Pushing down, right? You have a y component here. So that point has two components. By pushing down, you increase the friction. But this component here, push on the ground is going to... How come the box doesn't break the floor here? The normal force, right? It's called the normal force. We'll talk about it, but there is a support force. Let's call it the support force, right? The support force from the ground. You push on the ground is pushing back on you. You can think of the ground as like little spring here. You have little spring. So push, it's going to push back. We call that the support force for now. And what else do you have? You see, it's friction, right? Very good. You're going to have some friction. If I am able to overcome the static friction, then it will move forward, right? And then you have some kinetic friction, but it's going to be hard to push. That's the idea also of the sled. You know, there is, I don't know what it's called, but some people, they have a rope here and they pull on the sled at the gym, but you have a lot of friction. That's the idea. You have a lot of resistance. So the net force here, the net force will be my push along the x minus the kinetic friction. That will be your net force. Okay, and from there, you're going to get the acceleration. Up and down, it's not going anywhere. They're going to kill each other out. They're eating each other out. So up equals down. Along the x-axis, if this one is larger, then I will be able to accelerate the box. Is that clear? What's going to happen if my push exactly match the kinetic friction? So force is not going to go anywhere, but if it matches, so first I have static friction, and then what happens here? An acceleration? Are you sure we have an acceleration? An acceleration? Constant velocity, because the net force equals 0. The x component equals the kinetic friction. Now, if I overcome, then there is an acceleration, right? My back hurts now. Okay, so let's do this one now. This one is easy. Okay, you need to find the x component and the y component. We did many of these. Let's do this one quickly because we did a lot. I mean, if you do your assignment, we did a lot. I don't know who is talking in the back over there. Shh, quiet. Okay, now you can talk, but after that you stop talking. Find the x component and the y component. The magnitude is 160. Okay, so what I recommend to do, you make a cross at the tail. So that way you see in which quadrant it is. 1, 2, 3, 4. And then you make another cross. So it's going to be the fourth quadrant, right? So now you know it's in the fourth quadrant and it's down. So you attach the tail to the origin here and it's down this way. And then a little bit of geometry. If this is 55, that's not very helpful. So we're going to put our 55 here. Okay, so because you want the angle relative to the positive x-axis. And then from there, you can use your trig. Okay, it has an x component that is pushing forward. Okay, so that will be your x component. And then it has a y component which is pushing downward. So it has two components. That point here. And then either you do, so the magnitude is 160, so it's a review, right? 160. That's the magnitude. Okay, so x component, either you know your trig and you go 160 cosine 55, or you don't know your trig and you remember that I said that if you take the angle from the positive x-axis and you go counterclockwise, then x will be always cosine, so that will be 305, and the y component will be always sine. Otherwise, you can say sine 55, it will work, but you want to make sure you have a negative. Is that clear? Uh-huh. So that will be 92 Newton minus 131 Newton. Do you all agree? Okay, and then you will have to look at the other forces. So obviously you're going to have the weight pulling down, and you have the support force here, and you're going to have some friction. If it's moving, it will be called kinetic friction. If the x component is larger than the kinetic friction, it will accelerate. Otherwise, it's moving at a constant speed. Okay, so here are the laws of Newton. Law of inertia that was introduced by Galileo. Newton's second law. F equals ma. Newton's third law. For every action, you have an equal and opposite reaction. First law is not intuitive, and it was explained by Galileo. It says if something is moving, you don't need a force to keep it moving. It wants to keep moving at the same speed in the same direction forever, ever after, right? Mm? Yes, so inertia, exactly. So if the Earth was not here, the moon will keep going in a straight line at a constant speed forever after. So if you have a plug on a puck on the ring, on the ice, for example, you push it, it will keep going in a straight line at a constant speed forever after. It's not that intuitive. So if an object is at rest, it wants to stay at rest. And if it was in motion, it wants to stay in motion at the same speed along the same direction unless acted upon by a force. Okay, so this is called the law of inertia. And the best way to understand the law of inertia is this. Okay, so if you do not have a seat belt, so the dummy here is moving at the same speed in the same direction as the car is gonna crash. What's gonna happen to the dummy? Exactly. It will keep moving at the same speed in the same direction until it's gonna hit the windshield and it's gonna like this, right? It's gonna break your neck. Boom. Oh, that hurts, right? So only the car is acted upon by a force. Your body here or a body here is not acted by a force. No seat belt. No, now it's good, right? They did test. And here you have some definitively not the same situation. So here, not only you're gonna apply a force to stop your body, but it has some yield. So it means even though the change in momentum will be the same, you stop from moving here because you increase the time it takes to stop, you're gonna decrease the force. So it's not going to be as bad as with a seat belt. Seat belt is just you stop, right? It can hurt. Okay. Now inertia again is what is called the laziness in changing the state of motion. So if you are going along a straight line at a constant speed, the laziness, the inertia is just the mass. If something is rotating, the inertia has to take in account the configuration about the x-axis. But along a straight line, is the inertia is just the mass, and the unit is in kilogram. So it means that for the same force that you apply, a larger mass will not experience the same acceleration. The acceleration obviously will be smaller. It's not going to react the same way. Okay? It's not that intuitive. It took 2000 years after Aristotle. Aristotle disagreed with that. He said that things stop from moving because they are lazy. So here is a typical misconception. Motion requires force. That's not true. Something in motion wants to keep in motion at the same speed along the same direction unless acted upon by a force. So a force causes speeding up, slowing down, or turning. Okay, so you have many experiments you can do. So this is also inertia, because what's happening, if you do it very quickly, okay, you only have kinetic friction, and kinetic friction is very small. So if you do it very quickly, the force does not have time to be to build up enough that it will oppose the motion. So it means because of inertia, you will be able to do that trick here. But you have to do it very quickly because those have inertia. So let's see, the tablecloth. You can try that for extra credit, not this one. This one. It's good, you get excited, right? So all those masses, they have inertia. They don't want to move unless acted upon by a force. The force that is acting here is not static. So if you go very slowly, it's static friction, which is very large, and those will go with the tablecloth. But if you do it very quickly, that will be kinetic friction, and kinetic friction is very small. Okay, so it's not large enough to fight against inertia. Okay, and there is a video that used to it's not anymore on YouTube, but when I see something I catch it. But it was a video that made the buzz. Is not good.
In this clip, a cable as long across and central bank carries hidden block settings without discerning super motorcycle. In this viral video, rather than a quick flick of the bridge, it's a quick flick of the accelerator. Off disappears, and a perfectly laid table remains. Turbocharged trick true, or just special effects sorcerer. All set, ready to run Christmas dinner? Can't wait. Uncle Jamie always does that. Get started.
So at the end, he figured it out, and he's able to do it. What's the trick? The what? So first of all, you need a lot of oomph, right? Very large acceleration. But he did it. How did he do it? Very large impulse, but what else? What did I tell you? You want to make sure that the static friction is very small and only kinetic friction applies. So what did he do? He put something on the table, right? He put some wax here, right, to make it very slippery. So that way you decrease static friction and only kinetic friction will apply. Okay, so that's something we're going to see. If you have kind of friction, so for example here I have a paper, my Perrier, of course. If I pull very slowly, you see, that's inertia and that's static friction. There is static friction between the Perrier and the paper. But if I do it very quickly, applaud. So that will be kinetic friction, right? Kinetic friction is very small. I'm proud, no? It's good. Okay, if you want to do it this way, definitively extra credit. So there is a lot of demo you can do with inertia. This one, if you are a handy person, student, you see if the hammer head here is loose, you're gonna take your hammer and you're gonna hit the table. Because why? That handle is gonna be stopped, but the head will keep moving by itself on its own because it was moving before, so it will keep moving at the same speed in the same direction, so it's going to secure itself. So this one doesn't give you a lot of extra credit because it's easy to do, but it's also very famous. Huh? Again, it has to be very quick to make sure that kinetic friction is involved, not static. And then this one is also very famous if you want to do it. Quickly. So what do you think? Which string will break? The top or the bottom? Bottom? Very good. Because it has inertia.
So,
Right? More on inertia. So because remember, we're going to see that if you want to change the state of motion, you need to apply a force during a time t. So if the time is too small, the force doesn't have enough time to build up and to fight against inertia. Okay, inertia here at school, it stays behind. So that's inertia too, right? It stays there and then it falls. And what else we have? Okay, so this is very famous. It's called winnowing. Okay, it's a technique, very old technique to separate the seeds from the dust. So you have a shovel and you throw the seed mixed with the dust. So the seed will be moving, but the dust has less inertia. Separate. So you have ideas if you want to do a demo. So that idea of inertia was introduced by Galileo, who came up one of the first to come up to come up with thought experiment in his head. So help me here. He said the following: Imagine this is supposed to be curved. Okay, so you have a ramp and there is no friction, so it will go back to the same height and then it will swing back and forth. Do you agree? No friction. So it has potential energy, kinetic energy, come back to the same height. So it always wants to come back to the same height. Okay? And then maybe it will go back. What's going to happen if I make it flat here? Very good. It will keep moving forever at the same speed in the same direction, like it's trying to find the same height, but will never find it. Genius of Galileo. He did that in his mind. So it's like a thought experiment. That's what Einstein did later, thought experiment. So this is the idea of inertia. Okay, typical conceptual question on the pop quiz. So if you have inertia, it makes it hard. More inertia there is, harder it is to speed up, to slow down, but also to change direction. Mass spectrometer, that's the idea, right? A large mass will not bend as easily as a small mass. Right. So if you have an elephant from Miami Zoo, by the way, if you go to the Miami Zoo, you get a discount from FIU. FIU. They give discount to FIU students. So anyway, so what should you do? You said it, right? So if an elephant is chasing you and you cannot go faster than the elephant, you should, right? You should go zigzag. You go zigzag, right? So there is something about those missile Stinger, and they are special missile going after airplane because they have infrared sensor and they feel the heat. So if they go after a drone, for example, or a small airplane, the pilot knows that it has to do zigzag because it's harder for the missile to always change direction. Needs a force, right? Now, here is a misconception. Of course, it's going to be easier on the moon to lift a mass because there is less weight. Is it easier on the moon to push a mass, the same mass, than on the Earth? Push, not lift, push. No, it will be as hard, okay? Because inertia will be the same. So you go to the moon, the mass will be the same. So it will be, if I take this to the moon, it will be as hard to push. It will be easier to lift, but as hard to push. So that comes from a very, if you like physics, it's called conceptual physics by Paul Hewitt. And it's a very nice textbook. Okay, well, we already discussed that. So if you want something to curve, you need to apply a centripetal force. So you have a bullet, right? Projectile, boom, 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 boom. Which way it's going to go? Three. Excellent. Very good. Three, right? It will keep going along a straight line at a constant speed unless acted upon by a force. So if you want something to change direction, you need to apply a force. So I don't know if I show you that. I find this very cool. You can try that at home. Same idea. Okay, things will if they were going along a circle and you don't have enough force to keep them on a circular track, off tangent they go. Off tangent. Kinetic friction. Not strong enough. Isn't that cool? And movie maker don't take physics, obviously. They didn't take physics 2048. That cannot happen. If you want something to curve, you need to apply a force. Nothing will curve on its own, right? That can't. No, not. Cannot be. That's not possible. Well, impossible. That will not happen. For something to curve, you need a force to be applied. However, it's true that you see those bullets, they are spinning on their axis. That's for stability, right? That, by the way, it will increase their rotational inertia. Okay? You have linear inertia, but something is spinning, you have rotational inertia. So because they are spinning this way, it will make them very stable, more laziness when it comes to drag. But this, no. Not possible. Okay, so which one is the natural tendency for an object to remain at rest or in motion at a constant speed along a straight line? Inertia, very good, right? Inertia. We all have inertia, by the way. Like most of you, when you come here, you always sit at the same seat, right? Because you want to save energy. So it's too much thinking, oh, should I sit here? This guy I don't like, or this girl I don't like. Oh, I'm gonna no, too much work. So this is called inertia. Okay, so we already talked about that, and I told you about the mass spectrometer. 1941, Ernest Lawrence, California, he came up with the idea to use a mass spectrometer to enrich uranium. And since some of you are taking chemistry very seriously, I have biochemist student. You see, uranium-238, uranium-235, which one has a larger mass? 238, right? It's the mass number. So it's isotopes. And you learn in chemistry that because it's the same element, it's uranium, you cannot come up with a chemical reaction to split them apart, right? You can't. They will react, they will behave exactly the same way in a chemical reaction. So the only way you can do it, for example, is one of the way you can do it. It's not the only one. That was the first one they did it, is to use, right, to use the mass. Exactly. Okay, so this one has more inertia, so it's not going to bend as much, sorry, than uranium-235. But they had to do it over and over and over and over again to get enough uranium-235, because to make a bomb you need uranium-235. And then nowadays they use different techniques. They use laser, they use other techniques that I forgot, centrifuge, but that was the old way. So that's why physics is relevant sometimes. And then you have Newton's second law, right? So Newton's second law. So Newton's second law was written this way. So if, remember, Principia is the most important book in physics. It was written by Isaac Newton. And in that book, he wrote the following. If you apply a force during a time t, then the momentum will change. Or if there is a change in momentum, then there will be a force over a time t. Change in momentum can happen only if there is a force applied during a time t. Change in momentum meaning spinning up, slowing out, slowing down, or turning. Okay? So what is momentum? It's a quantity defined by Newton, and he called that the quantity of motion. How much motion there is for mass. So the definition of momentum, which is a vector, is just mass times velocity. Okay, that was defined by Newton. He called that the momentum, the quantity of motion. We call that the momentum, but he called that the quantity of motion, right? So if there is momentum, then a force can be applied. Okay, and this is a delta. Delta means change. Change means final minus initial. Okay, so apply a force during a time t, then there will be a change in momentum. So I can take the mass out here, delta V. So force equals m delta V over delta T. And what is delta V over delta T? Acceleration, very good. ma. That's how you learn. In textbook, you always learn F equals ma, but it should be more like acceleration is a force per unit mass, and sometimes this is more relevant because you apply a force during a time t, then there will be a change in momentum. If there is a change in momentum, there is a force applied. Okay, so for example, very quickly, okay, if there is a change in momentum, moving stop is like boxing, right? Force, change in momentum means force. you will be 100. So change in momentum from moving to stopping, there will be a force times t. If the time is small, the force is huge. That's the idea when a jab, for example, in boxing, huge momentum, small time, huge force. Change in momentum is force times time. Okay, so Tuesday we have a test.